2 weeks ago, my brother challenged me to make a bridge that could hold our 2-week infant baby. She's now 3 weeks old.
Brick stud.
So here is baby Lily. She's 3 weeks old. This one's for you, Mark. We built it. Here we did it. Easy. Okay, but even better, we're gonna put our whole family on that bridge. Let's go. Okay, sit down.
It's not breaking at all, Ken.
Andrew, come on.
It's not gonna break. Come here. I'll hold your hand. I'll hold your hand too.
No, I'm just gonna have him hold the baby.
Don't drop her.
What do you think? Should I sit on it?
Yeah!
Yeah!
No!
No!
No, it's gonna break!
Oh, oh snap.
Back up, Ken. I actually don't think it will.
I think it's gonna break. Oh! And I'm done.
Over here is where it broke.
Oh, they just popped out. That's actually held pretty well. If I just add some more of these things, it'll stay together. I'll be back with repairs and then I'm sitting on this thing. You want to see if it's gonna break?
Yeah!
It's going to break. Carly, I'm sitting on it. It's not breaking. Oh, it didn't break. Pull your pants back down. Your legs down.
No,
You guys want to sit on it with me? Come on! Because I don't think I'm going to do this again. Come on, Cameron. We did it! Let's talk about the design of this bridge for a little bit. So there's a couple ways that bridges or beams can break. Because they're bending, we're going to look at a couple of those different forces. So if we looked at the top of this, initially it would be a certain length. We could measure that length. Once we apply a forces on the top, it'll start to bend, it'll become concave. If we measured the new distance, we would see that the top length is actually getting shorter, it's getting smashed together. That means that in the top here, there are forces that are compressing it. Another way to think of it that would make it even more apparent is if you stuck 2 sticks or pencils up on the top. Initially, there's a distance between those 2 sticks. As you bend it, they would bend in toward each other, telling you that the top is in compression. That's one way that this can break, is in the top, this will crush or buckle along the top surface. Conversely, down on the bottom, we could measure this. It would have some original length. Once we bend it, it would start to have a convex curve, and the bottom would actually be getting stretched out. That means that the forces down in the bottom of the bridge are in tension. So that's one way that this could break, is in here, one of these sections, there would be too much tension and the bottom would rip apart. Another way that this can break is on the interior. The interior will be breaking due to shear forces. Shear forces are forces that are causing atoms to slide apart from each other this way. Instead of smashing together or ripping apart, you're getting atoms to break in a sideways motion. The forces for each of these are highest in different locations on the bridge. So the highest places where there's bending, the highest tension and compression will be in the middle length of the bridge. This is where the bridge will be the curviest, which means they will have the highest compressive forces and the highest tension forces. So a way to build a bridge efficiently is to have higher strength in the top and bottom of the bridge, right in the middle of the bridge. The shear forces, the forces where the blocks are wanting to move apart from each other this way, are going to be the greatest in the ends. So you want to have stronger interior sections at the ends, and in the center, you actually don't need as much strength. That's why I had some of these voids. I thought this is a way to save some blocks so that I could build it taller and hopefully not run out of all of my blocks so quickly. One more point is making sure that the entire bridge is one uniform section. So these sections on the outside are just holding the sandwich together. They're holding the top and the bottom. I want the whole thing to bend as one unit, not as a bunch of layers. Here's a quick example of how that works. So I got a paint stick. One paint stick bending is a certain amount of flexibility. If I took another paint stick and just set it on top and started bending it, it would be twice as stiff. But these two paint sticks are able to slide apart from each other. So as I bend them, it's essentially just two sticks stacked on top of each other. If I took staples or nails, nailed this together or glued it together so that it was one piece, it wouldn't be twice as strong. It'd actually be 8 times as strong as one. So by gluing the two together, two glued together would be 4 times as strong as two simply stacked on each other. Earlier, you saw me sit on this and you saw it start to break and pull apart. That's because these were popping off the sides, and now instead of one single unit, we are getting just bending in the top and bending in the bottom. And that was because the two layers were separating from each other. So those are the things that I thought of while building this bridge. And that was kind of the thought process behind why it is the way it is. If I wanted to make this significantly stronger, what I would do is make it increasingly taller. That would resist the bending forces. I would increase making sure that it was one solid unit. And if I really wanted to make it better, I would ignore the bending completely and I would go more like a stone construction, a big stone arch. That would be the strongest possible design that I could think of, because then everything would be in compression, and Lego blocks in compression are really strong. So it'd be kind of like a stone building. In stone building, they just stack a whole bunch of blocks on top of each other. Everything is compressed together. That would be the strongest design that I could think of. But I didn't want to do that because that seems less engineering. This seems more complicated, to have something that is just supported on the ends and just bending. Thank you so much for watching. Till next time, keep building.